Welcome everybody to the final session of this workshop. Our next speaker comes from TIFR Mumbai. He has done beautiful work in many areas at the intersection of probability and computer science. For a sample of his work, please welcome with a round of applause, Piyush Srivastava.
This talk is over. So thanks. So as we're talking about sampling from convex bodies, this is joint work with Hari, who you heard already, and Amit, who was at IIT Bombay. He's just finished his undergrad there and he's moving to MIT. This was his undergrad. This is part of his undergrad thesis, if I recall correctly. So the problem is very natural. You're given a convex body specified in some way, and you want to sample a point approximately uniformly from the body. So this arises in many applications, but we'll be looking at it from a very abstract kind of perspective. So all we want to know is how is the how is the convex body given to us. So there are many natural ways it could be given, in which it could be given to us. Perhaps the most sort of general is this something called well-guaranteed membership oracle, which says that given any point, I have an oracle which will tell me whether the point is in the body or not. That's it. And in the beginning, it also will tell me that the body is contained within a ball of radius capital R and contains within it a ball of radius small r. What does this mean? This means that the body is not too thin. It's not like a flat, like a dosa kind of a thing. So that could be hard. That could be hard to sample from because you might get stuck at a corner. So and the other one is just for scaling. So you can pick one of those two, and the other one is just to keep the scales correct. Okay, but there is another interesting case, which is polytopes, for example, which could be given a different way. They could be given by the linear constraints that define the polytope. So that's another, just to give an example, another setting where the membership oracle might not be. You can implement the membership oracle, of course, for a polytope, but you might have more information. But we will be looking at this membership oracle model, so general convex model. And our requirement is that in time, or number of operations, number of steps, that is polynomial in the dimension, n is the dimension, n is always going to the dimension and stuff. And this so-called aspect ratio, which is the ratio of this outer ball and the inner ball. Okay. And logarithmic in 1 over epsilon operations. We want to produce a sample that is within epsilon statistical distance to the stationary distribution. So that's the goal. Okay. So any questions about the model? Yeah. No, so I'm not thinking of fault. So this is for a general convex body. So what this is saying is that you are not allowed to have something of this kind. This is sort of convex up to my drawing skills, but it doesn't. The R, capital R by small r for this will be huge. So that's. This is high aspect ratio. No, this is more than that. This is much more than that, right? I mean, because the aspect ratio is saying that so interior is not empty, is just saying it's a body. But here, if you're saying that not just that, it's like it's not too flat. Okay, so yeah, so but that is all captured in the fact that our running time is allowed to depend upon the aspect ratio. If you start making the body flat, this will become infinite, and so the bounds will lose all meaning. Okay, so the usual idea for this kind of problems is to run a random walk on the body, some kind of a random walk, and hope that it mixes fast. So hope that it gets to the stationary distribution fast, and the stationary distribution of the random walk is supposed to be the uniform distribution on the body. So there are many examples. In fact, the first time something like this was actually done was the seminal paper of Dyer et al., Dyer, Fries, and Cannon, which was based on putting a uniform grid on the body, and then doing a random walk on the body, and then doing some lot of pre-processing and post-processing to get a sample out of this. Another, maybe a more natural algorithm is ball walk, which just is exactly what it sounds like. You're at a point in the body, you have a fixed radius ball, like a sphere, like a spherical ball. You pick a uniformly random point in the ball. If that point happens to be in the body, you move to it. Otherwise, you just stay. Okay? So that's the ball walk. We'll be looking at something that is different from this, but towards that, there's hit and run. So hit and run, I don't know where the name comes from. It's already described in this old paper, which I'll have referred to later also. And it does the following. So you are at a point in the body. This is the current state. You take a uniformly random direction. So, and then you draw the chord of the body in that direction. So that's the uniformly random chord. So the chord is taken uniformly at random. So the direction is uniform. Then you take the chord. And then on the chord, you pick a uniformly random point. So that's one step of the walk. So it can make large steps, unlike the ball walk, which was sort of limited in how far it could go. This can go far. Okay. And so this is one example. What we will be concerned, one of the walks we'll be concerned with in this talk is something called coordinate hit and run. This is actually even older, depending upon how you look at this paper. And this does the following. It's similar to hit and run, but now instead of picking a uniformly random direction, you pick a uniformly random coordinate direction. And then you pick, then this is the same. You pick on that chord, you pick a uniformly random point. Yeah. Using what? On the chord? Oh, yeah, so you can do binary search essentially. So you can figure out the length of the binary search and then. Okay, so that's the thing. So coordinate run, yeah. So, but this, as you can realize, this is not a trivial operation. So you have to figure out the length of the chord. So that's why coordinate run was. So I'll come to that later. Even in this old paper, they were already claiming that this seems to be more easy to implement and more efficient in practice, because especially for polytopes, it's easier to figure out the endpoints. But we'll come to that later. And there are many things, many other walks that we'll not talk about. So you should always talk about things that we'll not talk about. So one of, like, Hamilton Monte Carlo and its derivative. So we want to prove fast mixing, and for what? So unfortunately, we cannot always hope for rapid mixing. So I'll take a short detour. And one issue about this is the appropriate starting state. So for this, it would be useful to have some notion of what the initial state looks like. So we'll use this notion of warmth. So this is a little bit of a mouthful. So the initial distribution, so the initial point is also chosen from some random distribution, possibly, even if it's deterministic, that's like a delta distribution, Dirac delta distribution. So we say that distribution is M warm if its density with respect to the actual final distribution that we are trying to sample from, is bounded above by M. Okay. So M being large actually is less warm. So that's a bit of a misnomer. But so the issue is that if we have, so this M warm, the way it shows up in mixing time bounds is that if you only have a mixing time bound, so this is the number of steps the chain has to run to get to epsilon. If the dependence upon this warmth parameter is polynomial, then we only get rapid mixing from so-called warm starts, where M is small. This means that the initial distribution is already quite diffuse. It does not concentrate on any part of the body too much, okay? Only up to polynomial factors. What we would want is something, we would want to handle cold starts. Cold starts mean that our mixing time bound should be logarithmic in the warmth parameter. Okay? So just to keep this grounded in some pictures. So a cold start is something like this, that so like the coldest possible start is that you're starting at one point. That's really the coldest start. Of course, that is not covered by that kind of a mixing time. Often those kind of mixing time bounds can be massaged into this coldest possible thing as well. Okay, but really, like, other colder things would be like this. So you have like very peaked points at some distributions, and a warm. So these are cold starts, and the warmth. The warmer things would be that it's sort of diffuse. So somewhere here. So okay. So let's just look at because this is a story we'll be talking about. So some like a little bit of the story of the warm versus cold starts. Yeah. Yeah, so many of those things you can, so sometimes you can get, so usually, like, we'll come to where this shows up. So as long as you have some kind of, not density bound, but maybe some kind of initial bound where either L2 distance or something can be bounded well, but usually the only way you can bound them is with the density. So that's why I'm just talking about. Yeah, so so it's actually a non-trivial process, but it can be done. So in fact, already the old the Dyer paper was essentially doing that, and so this has it's non-trivial. It requires doing something else, some pre-processing on the body itself before you can get. Okay, so a variety of random walks have been studied, and so let's take just 2 examples. So hit and run. The first polynomial mixing time was by Loash, 99. It's a beautiful paper. So we'll not look at it in detail, but it got this Wormstad type mixing time. So the dependence upon the Worm parameter was M. You see what was the issue. And then later on, in later work, Loash and Webpala showed that they could also get, for the same random walk, cold start mixing time, so logarithmic in the Worm parameter. Okay. So we'll come to these terms later. So this was via something called an S conductance lower bound. This is something via conductance lower bound. So we'll see what these things are later. For the coordinated and run, so this, as I said, it appears to be quite efficient in numerical implementations. Already in 1984, Smith, in a paper which is not about sampling from convex bodies, just from sampling from arbitrary things, so was already saying that this is easier to implement, more efficient, because finding out the length of the chord is easier, sort of, when you're doing so, because usually the body will be specified by some constraints, and the constraints are in terms of some coordinates, so it's easier to check just by while you're varying one coordinate how far you can go in each direction. So so for this, but somewhat surprisingly, even the fastmix from Wormstad was open until recently, and then around 2 years ago, 2 papers around the same time. You have 2 different proofs for mixing from Wormstad for this. But cold start had still not been established, and it seems to be quite different from hit and run. So hit and run has a nice property of, because remember, hit and run was uniform. The step was uniform across on the sphere, right? So the direction was uniform on the sphere. That is not here, so that some of the mathematical elegance is lost. So the fast mixing from cold start for this was not. Okay, so as I said earlier, so this is so achieving a warm start may require significant preprocessing, but cold start is really trivial to achieve. So the coldest possible start, like 1 point, of course, are trivial. You have to start with a point in the body, and even otherwise, the way I define this well-guaranteed oracle, because you're told this small r ball is in the body, so you just sample uniformly from that ball, and then you get a because it only requires something exponential in, and that's good enough. So cold start is really easy. You just sample from the inner ball. And ideally, of course, so this is just recap. So ideally, you would like to change the mix starting from any point, and that it's not like sort of a direct reduction, but usually if you have that cold start mixing time, you can massage it a little bit to get this also. So now after this, let me come to the result. So any questions up to this point?
That the cold start, you can start from a 1 point, right?
Yeah, so that's the coldest possible start. Yeah.
Yeah. So I'm saying that infinity. So what can be the maximum size of subset from where you can start a cold start? Like
maximum size?
Like it can be small. It can be a small, very ball where you can sample a cold start, right? Not only a point.
No, so I mean, if it's already a small set, which is not a point, then it already has some measure, and if the measure is large enough, then you get a finite value of m. What I'm saying is that if you have those cold start type results, then you could start the chain from almost any point, which is not too close to the boundary. Too close to the boundary, there can be other like sort of technical issues, but if you're reasonably somewhat far away from the boundary, you can still get a cold start. The reason this happens is because you just run a few steps of the chain, and then it already has some little bit of mixing, which makes this distribution cold in the sense I said earlier. Yeah, so that is something you can try to do, but that's not the random. So again, that becomes part of this pre-processing. So we want to do everything with just one random walk. So that's yeah. So then you start fighting about which one is more. But this is much more significant. Yeah, conceptually, yeah. This once you have the cold start thing, it's not. Yeah, the warm start thing this is much more. Okay, so now the results. So So what the first result will actually be about different from all the Markov chains I've been talking about. We'll give a different Markov chain or a different family of Markov chains for sampling from convex bodies. And these are based on a very classical idea, which has found a lot of use in various branches.
Let's start. Ready.
Okay, so so let me now get to the results. So the first result is actually a different family of Markov chains. So as Sandeep was trying to tell me, this should have been studied before. I don't know why it was not. So this Markov chain is going to be on something called the Witty decomposition. It's a very classical object, has been used in for several applications. It's very useful as just a tool, an analytic tool. So what it does, so this is in the special case of convex bodies, but it can be done in more generally. So we decompose the body into a collection of dyadic cubes. So what are these dyadic cubes? So they are just, so think of the like the integer lattice and think of all its scalings by powers of 2. So both, like, actually we don't not need the expansions, only the contraction, but just all the powers of 2 scalings of the integer lattice. And a dyadic cube is one of the sort of the cubic cells in one of these. Okay, so we decompose them in the body into these dyadic cubes with the following properties. So that's what the Witty decomposer says can always be done. So where each cube in this decomposition has size, its side length, which is close to its diameter. Close to its distance from the boundary. So formally, the distance of any point in the cube to the boundary of the body is within a constant factor of the diameter of the cube. Okay? So the side lengths, in some sense, they're comparable to the distances. So that is one thing. So as you come closer and closer to the body, the cubes become smaller and smaller. And also, the local geometry is not changing very drastically. So any 2 adjacent cubes differ only in their side length by a factor of at most 2. So either they have the same size or one of them is half the other in terms of side length. So this kind of a decomposition always exists. And in fact, it can be sort of algorithmically found lazily. So at any point, at most points with probability 1, I can figure out the point. So most points will lie in the interior of some of these cubes, one of these cubes. And you can algorithmically figure out, just using sort of an oracle which can compute distances to the boundary. You can figure out which cube, what is the cube in which that point lies. You can construct that from this decomposition. So this decomposition exists abstractly. You don't have to compute it in advance. You can compute it on the fly as. Okay, so now that you have such a decomposition, so this is a classical object. What's the natural Markov chain? So the Markov chain is also natural. It sort of just follows immediately from. Because in the end we want to sample from the body, so the Markov chain has to be something like this. This is a Metropolis filter version of it. That we have a current state, so our states will now be cubes, these cubes, and each cube should have a weight that is proportional to its volume. So what should we do? So given a current state, the way we transition to an adjacent cube is the following: you propose the move to Q, and how do we propose the move to Q prime? We just pick a point uniformly at random on the surface of the current cube. And we propose to move to Q prime. This lies in Q prime, that point, and then we accept a certain probability. Okay, so you accept the proposition, this proposal with probability 1/2 times the minimum ratio 1 on side. So this is the usual Metropolis filter to make the chain reversible. In the end, the transition probability looks a little bit like this. That expression is not so important. The point is that the chain itself is also not so complicated. Once you have the decomposition, this is the natural chain, or this is one of the most natural chains. This is just the usual. Sorry? Yeah. So you are at a current cube. You want to move to one of the adjacent cubes. So what are these adjacent cubes? So there can be many such cubes. So for example, here there could be like actually exponentially many on this side, and there could be. No, so our states are now cubes. Yeah. So we are always on one of the cubes. So how will we sample from the body? Well, how should we sample from the body given that we have a cube? Yeah, we pick a point uniformly at random from the cube. So if you have close into the correct distribution on the cubes, then this will also be close in the statistical distance to the distribution on the body. So suppose that I'm not drawing this part. So now you pick a point uniformly at random on the surface. So suppose the point lies here. So then you're proposing a move to this. Now you have to either accept or reject this. So you have to accept or reject based on the stationary probabilities. That's what this ratio is doing. Sorry. That's what this ratio is doing. So this is to just maintain reversibility. So because you want that the stationary probability of this cube should be 1 over 2 to the power of the dimension times the stationary probability of this. Side length is half. So there's no sampling in the volume. So there's a cube. I want to move to another cube. From the body, yes. So yes, I asked the question, right? So suppose that I have a sample from the cube distribution. So I have a distribution on cubes where the distribution of where the probability of each cube is proportional to its volume. Suppose I have a distribution. How do I now sample from the body? No, you just sample from the cube. You've sampled the cube, now sample uniformly from the cube. So that's the thing. So now so that is the easy thing. So we have now changed the problem to sampling from the cubes, just sampling the cubes. Because if we sample from the cubes, we can also sample easily from the body. And now I'm describing a chain on the cubes. The state space is now countable. It's just these cubes. Well, I mean, that is not need. I mean, it's like that is just there, right? Because like I have a Markov chain. I mean, I have a distribution. I want to design a reversible Markov chain. So how do I do this? I mean, you do Metropolis filter. That's all. Sorry? No, so because that is already taken care of by the fact that you are doing this surface area thing, right? So yeah, so when you take these three things, both of these into account, that dimension factor gets taken. Yeah. Yeah.
I find a cube which contains the body overlap.
No, that is not at all the thing. So yeah.
That could be one algorithm.
Yeah.
I find a cube which contains the body in
Yeah.
a way, and I keep on refining it until I finally am fully inside the body, and then I take a point there, and that's fine.
No, but that is, yeah, so that you can try to analyze. That's rejection sampling, and that is usually not, I mean, in the very first step, how do you know where to move? Because the body will usually be a very small fraction of that cube.
That will be a bad
That usually, yeah, it's hard to make it work. I mean, it potentially something of more adaptive can be made to work. This is not it. This is not rejection sampling. We are starting in the body. We are in the body, and we take a random walk inside. Okay. Yeah, so for Praneeth's question, yeah, so because of the surface area terms, the dimension factor. Okay, and so the main theorem is that if you have a convex body with the same well-guaranteed oracle, so it's slightly different guarantee. So I write that well-guaranteed oracle in a slightly different form. So because there are these Markov chains can now be parameterized with the LP distance. So which distance I'm using to define the Whitney decomposition. So remember that here when I was defining this, whichever I could use any LP distance I want. And so for each of those, the chain is similar. And so for each of those chains, I have a mixing time bound like this. So the only difference is the capital R is like, which is the big cube, like the radius of the big cube containing the body. But the inner thing, I'm taking just a small BP, LP ball cube. So the R radius LP cube is contained in the body, and the capital R radius L infinity ball, which is the cube, and contains the body. And then the mixing time is polynomial. So it's like, you notice that the best one is M infinity. And polynomial dependence on the aspect ratio as well in this form, and logarithmic in the warmth. Okay, so that's the result for this chain, and it goes through conductance. So we'll prove some conductance bond. Sorry, we'll prove a conductance bond from which this will follow directly. So I'll come to what that is. So, and a corollary of this result after some extra work is the mixing time, cold start mixing time for coordinated as well. So I mentioned that this was open. So, if for any convex body for which now this is again the same things again. So it's a small r radius L infinity cube contained inside the body, and capital R radius L infinity cube containing the body. Then starting from M warm start, the coordinated run walk has this kind of mixing. And there's slightly larger dependence on n. I think 9 becomes 11 if I remember correct. You can convert it into a mixing time from any point that is at least e to the minus n distance away. So very small distance away from the boundary. So as long as it is just this tiny bit away from the boundary, you have polynomial mixing time even from a single point. So any questions about the, very briefly, but I can talk offline also. Yeah. So I'll tell you what was missing in the older results and what the diad cube achieves. That is actually it can be described in one line. So I'll just do that, in a little while. Okay, so yeah, in fact, just in this slide. So the previous results showed warm start mixing for this, as I said earlier, using something called S conductance. So we'll come to what that is. And what we show is that, so one of these two proofs, the one due to Ladda and Vempala, can be extended using the analysis of our multi-scale walk to give a conductance bound for this coordinate run. So that leads to this mixing time bound. So in one line, the reason everything helps here is the fact that this previous work, this S conductance and so on, which I'll come to, needed to throw away parts of the body. So which parts? Close to the boundary. So some parts near the boundary had to be thrown away to do the analysis. This sort of comes at a cost. And the cost is really that you need a warm start. And the multi-scale, the main thing it achieves is it does not need to throw things close to the boundary. So that's where the advantage comes from. Then there's some more. Okay. So with that, I'll just move into a slide. Like this part, I can also go quickly over if everyone is familiar with it, but I just had some introductory slides. But any questions about this so far? Yes, I'll come to that. That's what I was going to come to. Okay. So what is this conduct? Sorry. Yeah. Sorry, which one? Yeah. Yeah, so so these two things themselves are incomparable. If I remember correctly, this one also is not completely worse than one of them, but I don't remember exactly. But of course, yeah. So the issue is in this M. If I remember, I think this one is something like n to the 7, but degree 4 here. This one is slightly different because there they assume this is L2 balls, etc. So things become a bit tricky to compare. So it can change between bodies. Okay. So just a bit of a primer for fast mixing. So the goal for sampling is for a random walk, and from appropriate starting state, you want to quickly converge to the stationary distribution. And starting from corners in the case of convex bodies can be bad. So for example, the ball walk can get stuck near corner. So I'll come to what that. So the analytical tool, one of the analytical tools for analyzing all of this is the conductance and related notion of S conductance. So what is the conductance? So think of doing the following experiment. You first pick a point from the stationary distribution. Okay? So that is X. And then you take a step of the random walk. Okay? So the ergodic flow of S is defined to be the event that the first point lands in S and the second point is outside S. So that's what this is saying. So you first pick a point with respect to the stationary distribution. The ergodic flow of S is the event that the point lands in S, but after you take one step of the walk, you land outside S. And the conductance is just the conditional probability version of it. So what is the conditional probability that given that you land in S in the first step in the choice of X, what is the probability that you land outside X after one step of the walk? Okay, so it's the ergodic flow divided by the volume of S. And the conductance of the walk itself is the smallest possible conductance of any of these sets. And for reasons that you can see, like you have to limit to sets of size up to half, because the ergodic flow of a set and the complement will be the same. So you don't want to worry about it. So that's the conductance of a walk. And why is conductance good? So high conductance implies fast mixing. This is a classical result in various contexts. This form is from lower Ramanujan. So if you have M warm start, then the total variation distance between the T after T steps of the walk decays exponentially with the square of the conductance. So square of the conductance plays a role of roughly the spectral gap. So that's like one set of Seeger's inequality. And M, the warm parameter, sits in. So that's so high conductance can be seen as a statement about isoperimetry. So it's about a statement of the form that sets with a given volume must have at least a certain surface area, because this moving out is sort of like a measure of surface. So the proofs of high of high conductors in this convex body sampling case often depend upon proving isoperimetric inequalities for appropriately constructed metric measure spaces. So that will come to see. But yeah, so how to start the walk question that I've been talking about. So one might expect from the definition that small sets should have large conductance, right? Because they should be easy to move out of a small. But sometimes this can be hard to prove just because of technical reasons. For example, I said that Lowasch's original proof for the mixing time of hit and run walk was only a warm start, and that was partly because the conductance proof had conductance decaying, sort of like conductance decaying to zero in the form that this happened. I'll come to later, and later work removed this limitation. So, and there can also be fundamental reasons. Sometimes the conductance might just not be there. So, for example, for the ball walk, the one that I described earlier, you can have small sets close to the corners where the conductance is actually small, even though that set has small volume. So the picture is something like this. So there's this, think of this very sort of pointed convex body somewhere here, and this set here has small volume. But if you have a point here, you pick up. So the only way to make a move inside the body is to pick a point in this very small sliver here. Most of the time you'll be sampling things that are outside and just staying put. So you'll not be moving away. So the ball walk might so it can happen that you just don't have conductance. So one way to get around this is the notion of S conductance. So this is what I was talking about. So this lets you sort of throw away some parts of the volume. So what is S conductance? So it's again similar. So the conductance was just the ergodic flow divided by the volume. But now, and then you took the minimum over all sets. But now you only take minimum over small enough sets, and then you remove S. So the removing of S is for technical reasons. But the point is that you stop at some S, and then maybe because your conductance is becoming very bad for small S, and so you're trying to throw away those bad sets, and then take some expression that is similar to the usual conductance. And so S conductance sort of, it helps take advantage of throwing away part of the body. So these small parts of the body, like the corner, which were causing you trouble, but it comes at a cost. So what is the cost? So this is the corresponding expression for how fast things mix with S conductance. So if you only have a S conductance bound, so for certain S, then the mixing time bound looks like M times S. So this term is just there; it's not decaying at all. And then there's a decaying term here, which is similar, but the crucial thing is this fixed term. And that means that now so usually like the way you would have S conductance is that your conductance sort of is decaying. So you will have something like, it's only like at sets of size S, it's only about S. And so there, if you do put in that here, you'll get that mixing time bounds will look like, you'll have an M squared or some polynomial in M, the form parameter mixing time. To compare that to the conductance where it would just be logarithmic. So that's the S conductance proofs. So the way they go by throwing away parts of the body that are problematic. Hopefully those are very small volumes, but that comes at the cost of having this requiring warmth. So yes, so that's the effect of the initial density. So if we only know that the S conductance is large, and which that would just mean that, I mean, large in the sense that the only reason we'll use S conductance is because it's getting to zero as S goes smaller. If you have something like this, then you'll have warm start mixing time. If you have a full conductance bound, then you'll have cold start mixing time. And so the hit and run, so for the example I gave, so now I can explain what that was. So Lowasch's proof for warm start mixing time of hit and run had a S conductance lower bound, and the Lowasch-Wempala proof for the hit and run walk had a conductance. So any questions about it? Yeah, so that let's not worry so much about that. Yeah, so this, I think, yeah, actually, yeah, yeah, so I think that is also a problem. In the warm start, I think that epsilon dependence will also be sometimes called, because the usual way to get logarithmic dependence is to say that your Markov chain, like you can just restart it again, but that you cannot do with a warm start. Actually, Could be possible. Yeah, but yeah, let me not say anything wrong here. So yeah, yeah, but this is just meant as an illustration. Like I just did one calculation for this, but the crucial thing that you get this m squared, and the reason is that there are terms here that are not decay. Yeah, so as I said, so let's recap. So warm start may require some pre-processing, cold start trivial to achieve, and previous examples you already saw, and so cold and this work is about getting cold start mixing times coordinate run via another family of Markov chains called that we call the multiscale. So in the remaining 10 minutes, I'll go a little bit over the proof method. So the main theorem is a restatement. Now that I have the conductance, I can write that here. So the main theorem was that this MP random walks that were defined for these Whitney decompositions with the LP now, they have this kind of conductance. So 1 over the aspect ratio times 1 over n squared times 1 over n to the 1 over p. And that immediately translates into this kind of mixing. Okay. So one thing I'll say here that so the best one for this mixing time is m infinity, but that's also the hardest to implement. M1 is the easiest to implement and also has the worst mixing time of all of these. But for the analysis, because if we want to just use it to analyze some other chain like coordinate run, then I can use any one of them, whichever is best for me. And so that's something to keep in mind. So at a very high level, the proof structure will follow the structure of many other results in the area. So which is to reduce the conductance lower bound to some actual geometric isoperimetric inequality in some appropriate metric measure space, and to prove that isoperimetric. So the question, because I said metric measure space, so what's the distance and what is the measure? So metric measure. So the measure is clear, it should be the uniform measure on the body, but what's the distance? And so this is this is where like part of the so this is one of the new things that was needed for doing this. So here is the intuition for what the distance should be. So our decomposition looks a little bit like this. The cubes are getting smaller as we come closer and closer to the boundary. So in terms of Euclidean distance, when we come closer and closer to the body, each step of the walk is covering a smaller length. But somehow we don't want to measure that as a small length. We want that is still progress because it has moved. So we want to like that small movement near the boundary, we want to count as more than what its actual length is. So we want the metric to expand these lengths. Okay. So one way to do this, and this turns to work out, is something like this. So we try to define a metric of the following kind. So this is informal. I'll make it formal. That the length elements at near a point x should look something like this. So the actual L infinity length distance near the point x, whatever that means, I'll write on the rigorous thing very soon. If it was a usual L infinity distance, this term will not be there. But that I divide by the distance of x to the boundary. Okay. So the distance is expanded by, if it's close to the boundary, it gets expanded. So to make it rigorous, what you say is the length of any differentiable curve is given by this. So this is just exactly the same thing written more rigorous fashion. And so now the metric is defined to be the smallest possible length of any set. Yes, so we'll use many of these things. So having a continuous distance helps for like doing analysis. But often, yeah, you have to keep this in mind that inside any cube, you can convert it into a L infinity distance up with a very good approximation factor. Yeah, so that will be used. Okay, and now the main result that underlies everything is this isoperimetric inequality, which says the following: that again the same situation, the body is as before, and if you have now the partition of the body into 3 sets, S1, S2, and S3, such that S1 and S2 are distance delta apart, but in this metric. Then the volume of the part that is in between, that is neither in S1 nor in S2, must be at proportional to delta and the volume of the smaller one. So I'm assuming that this one is the 1 less than half, and times this extra losses, which is 1 over the aspect ratio and 1 over the dimension. So yeah, so for other reasons, so the paper has some slightly stronger results for special cases. And one thing that is 1 over n, the 1 over dimension factor, can be dropped for really small sets. So actually, compared to the S conductance case where things can become bad, here you're in the more intuitive setup that conductance is actually becoming better for smaller sets. Let's not get into that. This is the so 5 minutes. So I'll just maybe say, where does the where does this GP metric come from? Like, why should you even believe that this should let you get to the conductance bound? So just to recall, the conductance is this. So it's the conditional probability of landing outside a set S when taking a walk, and when first choosing from the uniform distribution and then taking a step to the walk. And to lower bound the conductance, therefore we need to lower bound the ergodic flow. Right? So this phi k of S is fixed. So we want to lower bound this as a fraction of, as a proportion of the of phi. So we just start writing things down. So what are our sets? So now our sets are just subsets or just collections of these cubes. Okay, so we have these collections of cubes, and I just write down the ergodic flow, and I write down the Markov chain expression. So that is all fine. Nothing deep is going on, and even here there's nothing deep going on. Or the only thing I have done is use the difference between, use the relationship between side length and diameter to replace everything in terms of, diameter of the cube and its surface area with the, its intersection with the surface area of S. So S is the set that I'm looking at. Q is a cube contained inside S. So S is just a collection of these cubes. And I'm looking at the surface area of the boundary of Q. That's also boundary of S. So like Q might have some part of it boundary that is going still to another cube in S. That doesn't count. So only these parts are interesting. Okay, so that so far is good. So the only thing one thing we'll need quickly is that so the thing is that we have surface areas n minus 1 dimensional volumes here. Everything in our isoparametric inequality was sort of still in n dimensions. Everything was about volumes. So we need to go to the one dimension higher. So we need to do the sort of remove the limits, and that we can do via this. So we're just saying that a surface area is sort of like it's a usual kind of expression that the surface area of a body is like you take the body and you expand it a little bit and then take the difference and then divide by epsilon. But usually you put a B2 here. That's the correct surface area. We are able to put B infinity just because we are looking at, because both Q is the cube and S is a collection of cubes. So in this case, even B infinity works. Usually, in general, it won't work, but here it works. And now you do that. So this is just algebraic manipulations. And so for this expression, you have something like this. So the point is that so there is diameter of Q involved here, and so the only thing sort of that we do here is to say that for any x in Q, so by definition of these cubes, because every point inside the cube had a distance that was within a constant factor of the diameter, so we want to do something more uniform over the points. So instead of writing this diameter, so it's like this more discrete quantity, we replace it with this more uniform quantity where we try to replace the diameter of the cube by the distance of any point in the cube to the boundary, and so for this set, which is just for every point x, we take like this cube around x, which has side length 2 epsilon times the distance of x from the boundary. So for that, we can take this whole thing and use this expression here to relate it to the volume of Q epsilon minus S. So this is again some simple thing. And yeah, so after all this and just some little bit of interchange of summations, you get to this S infinity. So you get to the point where you say that the ergodic flow out of S is up to this factors, the volume of S epsilon minus S, where S epsilon is given by the following. For every point in S, so every point in every cube in S, you take x, and to that you add this cube of side length 2 epsilon times distance of x from the boundary. So it's like for every x there's a different cube, and you take the set of all these cubes. Okay, so yeah, so to make this very rigorous, I think you have to take V infinity open, but let's not worry about those. So you have this S epsilon set. And now, so that is fine. So now there is at least some volume that I can talk about. What is the connection to the GP metric? And this is where, but yeah, we'll just have a picture before that. So what is happening here is that there's this S, which is this red thing, and this S epsilon is like, it's this, the extra green thing on top. So sometimes where things that are close, things that are far from the boundary, it's thicker, things that are very close to the boundary, it's thinner, and so on. And the crucial thing is this, that when epsilon is small, and how small, it does not depend upon S or distance, etc. But only upon the dimension. When that is small, the distance of S from the complement of S epsilon is actually large in the GP metric. And so now that, we know that the volume of, so this S epsilon actually, the K minus S epsilon is actually far from S in the GP metric. So now we can use the isoperimetric inequality to get bound this, and that immediately gives the connection. So I'll just stop here and not give the sketch of the isoperimetric inequality or the connection to coordinate run. So yeah, so that in conclusion, so we have a new family of Markov chains for uniform sampling from convex sets, and it exploits this nice geometric properties of the Whitney decomposition, and it has, I mean, it can be useful as a family of Markov chains in itself that we have not explored so much yet. It's a new family, but as a tool already it's useful because it can prove cold-stall mixing time for coordinate run, which has been used for a long time. But there are many open questions. So one thing that we have been wondering about is if one can use multiscale decompositions for more general sampling problems like arbitrary log concave distributions. This n to the 9 bound is almost certainly not correct in the sense that it's probably much better. The correct right answer is much smaller, and we don't know what the correct answer is and what the technique to get there. One thing I can say that the conductance bound for M infinity is tight. So to improve the mixing time, so via this technique, maybe the only thing that can possibly improve is the translation from the conductance of M infinity to quantity. Thanks. It's hard to implement. Like if I want to actually implement the chain, then M infinity is the hardest to implement.
Hardest to implement in a computational complexity sense?
Computational, like in a sense, I need much more information about the body. Like just with membership oracle, it might not.
Oh, okay, I see.
L1 can be done.
Any more questions?
One question. The isoperimetric inequality that is there.
Yeah.
Is it stable to perturbations? Seems like it should be, right?
Perturbations to what?
Like some Holly-Stroop kind of thing.
Sorry?
Some Holly-Stroop kind of thing. If I perturb the body a little bit, like I do a non-convex perturbation on the body.
Or non-convex.
But it's bounded in L infinity. Like
I'm not sure because this thing, it moves distance close to the boundary to infinity. So it might not be correct in the sense that, I mean, so even in that perturbation, if you take a set there, it just might fail there. So I'm not sure. Like a priori, it's not clear.
Like even if the perturbation is like bounded in L infinity, like
yeah, because the perturbation will be close to the boundary or something, right? And that's where this metric is sort of going off to infinity. Sorry? Yes. Yeah. So I said, so given any point, as long as I know that, so with probability 1, the point lies inside one of the cubes.
Yeah.
And I can figure out what the cube is just by a binary search kind of operation, similar to the one you use to find the chord.
I guess in one direction you can do it. Like this has to be I guess like you have to find an inscribed cube.
No, I have to just find the distance, like L1 distance.
Okay.
So let's say I want to just do L1. M1.
Okay. Yeah.
I just to find
Yeah.
L1
Yeah.
and
Yeah.
then
Okay.
So that's why I said M infinity
There are
can be hard.
axes aligned, so
Yeah, M infinity can be hard, but M1 is fine.